Good morning, everyone, and welcome to whatever happened to those dinosaurs. During this session, we're going to be exploring the plight of these animals here, the namesake of this conference. We're going to be doing it with JavaScript. We're going to be learning quite a bit of data visualization techniques. My name is DiMarco. I'm an engineer at a company called Data.World in Austin, Texas. We're like a stealth company or something, so I don't even have to tell you what we're doing. But today, what we'll be doing is we'll be making a full-page data visualization from scratch. The project that we'll be doing today is something that I've created beforehand, and I broke it out into all the steps that I took to actually get to the final product, and we'll kind of be revisiting all those steps one by one. To do so, we're going to be covering D3.js, which is the library du jour for your really custom data visualizations. We're going to be covering dinosaur extinctions. More specifically, we're going to be covering the leading theory of the mass extinction event. We're going to be covering asteroids. And we're going to be covering data scraping as well, which is like pulling data off of some third-party resources so we can actually bring it into the browser and create our own visualizations based on it. And these are the high-level steps serially. So we start off with the why, which I was actually really happy that Rachel started off with like the why she's doing this whole game thing, because I think you've got to be passionate about what you're working on, especially if it's a side project. And the why for me is passion. And why asteroids specifically? I got excited about asteroids because of one particular asteroid called 2012 DA14. Has anyone ever heard of DA14 before? Yeah, it's awesome. I'm so glad someone's actually heard of it. DA14 was an asteroid that was discovered in 2012. That's why the name 2012 comes from. And it was discovered in like a telescope like this. I think this might actually be the telescope that had first found it out in Spain. But there's a series of telescopes across the world that are constantly looking at the sky, trying to find asteroids and things that might end up hitting us. And it found something very peculiar and weird about DA14, which was that it was going to make a very, very close pass to the planet Earth, like an extremely close path. So they came out with a press release like this, which the space agencies across the world usually do when there's something that's potentially hazardous. And this image actually, it's not showing up too good on the screen, but this comes from the actual press release. But there's a line that goes from the bottom to the top of it that's the asteroid's path over the course of about like 14 hours. And there's a big circle on the outside, that's the moon's orbit, and then there's Earth in the middle, and then there's the geosynchronous ring that's around that. So this asteroid is actually going to come between us and a lot of our satellites, which is extremely close for an object to happen. And it was supposed to happen on February 15th, 2013. And about 12 hours before, let's see if I can get over here. There it is. About 12 hours before this asteroid was supposed to make its close pass, this happened. Anyone remember this? This is out in Russia. This is an asteroid or a meteor entering the Earth's atmosphere. This asteroid was no joke at all. It wasn't even that big. It was about like 30 meters, they've estimated. But they say it was about like 20 to 30 times the amount of energy over like the Hiroshima nuclear bombs. There were over 7,200 buildings in 6 different cities that were damaged by this. And luckily no one died, but 1,500 people were sent to the hospital. There was broken glass everywhere. Shockwave was just absolutely insane. And there was a bunch of confusion when this happened, like immediately afterwards. We knew DA14 was going to come, but it wasn't going to hit us, and it was not going to be for another 12 hours. So the question was, like, did NASA forget to carry a 0 or something? Or like, what happened that we got hit by this? And what it turns out had happened was this was a totally untracked asteroid that we didn't know about. DA14 did, in fact, pass us unharmed, as calculated. Let me get out of here. So NASA released a statement that morning that said that they think it was a completely unrelated object, and that turned out to be true, but that led me down this path to find out about this NASA program called the Near-Earth Object Program, which is run by the Jet Propulsion Laboratory, which sounds really cool to say in a JavaScript talk. And what they do is they work with like a worldwide consortium of asteroid tracking facilities, and they provide a place to host all this data for us to see, and a bunch of the scientific data behind it. And they have a little table that you can filter on to see all the upcoming asteroid passes. This is what the table looks like right now. What we're seeing is like everything that's relatively close within the next 60 days. And there's only 3 that show up right there, so that's not like that terrifying. That's not reason to really like make a data visualization. And you can see some of the more details about the 3. There's the object, the close approach date, and the distance, and then some more scientific data. But if you switch the filter from the next 60 days to see what happened in the last 60 days, it looks a bit different. This is a lot bigger than the next 60 days, which is kind of terrifying. We didn't like run into like an asteroid cloud or something like that. This is pretty common. Every time you go to this page, there'll be about like 6 to 10 upcoming, and anywhere from like 90 to 120 that were just in the path that we just discovered, which means we're not really discovering these things until like they've just about passed us. And we may make these close passes and look behind us, and we're like, holy cow, that was an asteroid that almost hit us. And this happens a lot, almost every day. This isn't supposed to terrify anyone, by the way. This is where we're probably pretty safe. I am selling a little doomsday kit afterwards, so come talk to me. I've got coupon codes for everyone. So that's the why I want to create this, because I think this is cool, and I don't think most people will go to this page and change the filters and get a feel one table is bigger than the other and why that might be. So I want to be able to bring this data forward and kind of and show this. So the first thing I have to do is scrape the data from the website. So we're going to use two libraries. We're going to use one called Request and one called Cheerio. Whoop for Cheerio, I'm assuming, or and these Cheerio is basically like a jQuery for Node type thing. It's like a DOM traversal on the server side. If you use Python, you come from like the beautiful soup world of some crazy stuff like that. And what we do is we'll just grab the contents of the page. Luckily, NASA's website is nice enough to actually encode all of the filter, like the next 60 days and last 60 days, into the URL. So we can just go and fetch that. We load it into a Cheerio object, and then we want to convert that table to a CSV. So we'll write up a quick function, just grab the table, go in each of the rows, and then for each of the rows, go in each of the columns, and then pluck out the text in each of those columns. And we make this big multi-dimensional array, and then we print it to standard out. We're not doing anything fancy, like no like CSV library to like properly encode the CSV. So this might break one day, but this is kind of the cheap way to do it. And if you look real close at a convert to table to CSV, there's this line where I get the table, and then I get the 12th index from that table, which is like the selector that I'm using. And that might seem really brittle to people, like I'm just grabbing, well, first of all, there are way more than 12 tables on this NASA's website. This page is pretty old. And I couldn't use an ID selector because there are no IDs on this page, and I couldn't use a class selector or data attribute because there's nothing discernible about that particular table to fish it out. But either way, I think the selector is pretty safe because I don't think the website's been updated in like 17 years. And I don't say 17 years like completely randomly. If you look at the source of this website, there's this function called Y2K year they're still using. And it's not the lack of var and the global variables they're creating and leaking out that's making me think this is 17 years old. It's the Y2K year part that's making me think this is 17 years old. So this was probably added in 1999. I don't know how it's still there. It's an old website. Luckily, the database is constantly being updated. But we end up with CSV that looks like this. The first row are the column headers, which is nice, and then every row beneath that is just the data. So that's our scraping session. Now we'll go into loading. We've got to get it into the browser so we can start visualizing this data. So we'll start off with just a blank HTML page. We'll drop in an SVD tag, and we'll drop in D3. We'll make a call with d3.csv. So CSV has a built-in CSV parser that will actually like issue the AJAX request and then parse it for you back so you don't have to like have a third-party library. Everything we're going to be doing today is just D3. There's not any helper libraries. And then a .get, which is going to return an array of objects. And this works really nicely, except for if you look at like the HMAG, which I'll explain what HMAG is later, but it's a 27.2 like wrapped in quotes, so it's not that friendly as far as like discerning data types. So to do that, you can add a .row function beforehand, which is basically like our transform function, which it's a function that takes a row or it takes an object and returns an object. And you could do all of your parse int and your parse float. I'm even doing some parse date stuff with D3's built-in date parsing. And that's essentially it for loading. And now we've got it in memory. We're ready to drop it onto the page. So to draw it, the top of this continues from the CSV get and the transform. We'll call this function called draw asteroids, and we'll pass it this array of asteroids. We've got a commented version here. The bottom's a little bit cut out, but we append a G tag. A G tag is like a relative grouping tag. It's kind of like setting position relative on a div and then position absolute on all the child elements. We'll call select all asteroid, which is the asteroid class, which we know is going to be empty because we all saw an empty SVG tag. This is actually pretty normal. This is a little bit concerning when people are learning D3. This looks wrong, but it's actually right. And then we'll call .data, and we'll actually send it the array of data. And then chained off of that is .enter. .enter is like D3's for each loop. So for everything that was just added in that .data call, we're going to call whatever was chained onto that. And to do that, we'll just append a circle. We'll add a class for asteroid. So next time we call select all asteroid, we'll have something to return back. And then a couple of arbitrary values like the R and the C. It's at the bottom of the screen. I'll go back one. So the radius of 20, and then the CX and the CY of just some random variables. And it ends up looking like this on the page, where it's just one big dot in the middle of the screen. We can crack open the inspector. We can see we actually have one circle for each of our asteroids. So now the asteroids are at least there. We just haven't used any more of the data to actually draw these things. So we'll move into scaling. And scaling is, so the last 4 steps are drawing and scaling and drawing and scaling. Drawing and scaling is kind of like the rinse and repeat shampoo instructions of D3. You'll end up going through it quite a bit. I think scaling is one of D3's most powerful features. And D3 is not short on powerful features. I mean, we've already seen a CSV parser built into it and a DOM manipulation library built into it. It's got some crazy layout stuff. It has geo stuff and geometry. It's pretty amazing. But D3 scaling is really interesting. And the main point of this talk is to kind of talk about D3 scaling and see how we can use it to power like everything we need on this data visualization. And what the scaling does is it helps us translate numbers from the data's domain. So if you're working with like income data, you might have anything from like $25,000 to like $125,000. Like that's the data's domain. And it helps us translate that like to an example like coordinates for your user's viewport. So the viewport is from like 0 to 500 pixels or 1200 pixels or however wide the screen is or however wide the SVG element is. And D3 scaling will help us translate all those numbers consistently. And it can also help. I'm not going to be able to show all of the power of it, unfortunately, but it'll help you do things like even scale colors from like red to green and everything. It's got a ton of powerful features. So let's set up a problem statement. One lunar distance. A lunar distance is a measure that the astronomers use to calculate the closest point that the asteroid is going to be, or the distance that an asteroid is from the planet. A lunar distance is the distance from the center of the Earth to the moon, and it's about 384,400 kilometers. The moon's orbit is like slightly elliptical, so it changes, but that's the approximation. And a lunar distance is just it's a unit of measure. It's like an inch or a foot. So 8.5 LDs is about like 3.2 million kilometers. So given a 500 pixel high screen, where 0, 0, which is the top left corner, is 0 LDs, and 0, 500, which is the bottom left corner, is 10 LDs, solve for the right coordinate for 8.5 LDs. And this is pretty straightforward with D3 scaling. We'll set up a couple of constants like lunar distance and max LDs, and then we create this scale function. So we call d3.scale.linear, and we set up the domain, which is from the data's domain. So I want everything from 0 to 15 lunar distances. That's the amount of data I'm going to be giving it. And the range, which is going to be from 10 to like the height minus 10. So from 10 to 490 is like the acceptable range that I want to draw all these things in. And now I ask D3, when I give you a number like 8.5 LDs, tell me how many pixels that's going to be for a particular coordinate. So a couple of just sanity check assertions. Lunar distance of 0 is going to be 10. That's the lowest number in the domain. Is going to be the lowest number of the range. And the same for the opposite for the highest. And then 8.5 lunar distances is going to be rendered at 259.3 pixels. To drop this into the data visualization, it's pretty straightforward. We just change that the CY, which is a circle center Y coordinate, to instead of a static value, we're just going to call lunar distance and pass it the nominal lunar distance times lunar distance constant. Oh, there's the scaling function, and there's the part we want to update. And then it looks something like this. So we've moved in on one axis now, and we're getting a little bit better of a view of this data. They're not all on top of each other, but we still have, obviously, a long way to go. So another scaling problem. Today's date is June 24th, 2016. About 8.5 months ago is October 8th, 2015, give or take. So given a 500 pixel wide screen where 0, 0, which is the top left corner, is 1 year ago, and 500, 0 is 1 year in the future, solve for 8.5 months ago. That's a little bit trickier than the last one to do by hand, especially when you're messing with dates, and nobody likes to mess with dates. But D3 does, and it encapsulates it all. So we'll create a d3.time.scale. The domain is a year in the future to a year in the past, and the range is going to be from width to 0. So a sanity check is time scale of like right now. If it's a 500 pixel wide screen and it goes a year in the future, year in the past, we should be right in the middle at 250 pixels, which we are. A year in the past should be 0, a year in the future should be 500. And about 8.5 months ago should be rendered at 73.1 pixels. So we drop that into the CX coordinate of our data visualization, and now it looks like this. So we're getting closer. We're moving steadily towards it. And if this data looks wrong because one side is like all blue, like the past is one all blue, and the other side is kind of sporadic, like the exact point why we're doing this data visualization, because that's kind of the reality of the situation. Is most of the asteroids we know about are like in our immediate past. One more scale is going to be for the asteroid size. So the H magnitude, the absolute magnitude, that's it's like the amount of light that's reflected off of it. It's an estimate, but we use it to calculate the size of an asteroid. A smaller H value means a bigger asteroid. So golf rules here. So from a range of 0.75 pixels, which is like the smallest radius I'm willing to draw, to 7 pixels, which is the biggest asteroid, which we hope there are none on this page. We're an H value of, let's say 30, which is going to be the smallest asteroid, is going to be the smallest, and the biggest is going to be 7 pixels. So solve for an H value of 23.43. And the asteroid that hit Russia that day was probably around like 25.5 or so. It's an estimate. We didn't really get to see it beforehand to measure it. It just kind of hit us. So this time we'll use a logarithmic scale instead of the linear scale. There are a bunch of other options that you can use within D3 scaling, like square root, exponential, linear, logarithmic. It can do things, like I said, like colors and just a bunch of different values. So the smallest one should be 0.75 pixels, the biggest should be 7, and then the H value of 23.42 comes in at 3.47 pixels. And then to add that to our little function here, we'll override the R, the radius, which used to be hard-coded to like 10 or 20 or something, and now it's the size scale. Now we end up with this. So we're moving steadily towards a more complete data visualization. We've created 3 scales, the lunar scale, the time scale, and the size scale. And everything else we're about to add to this, I'm not going to show too much more of the code to add it, but all the code's available. This is all open source. Everything else we're going to add, all of like the ticks and the labels and all the contextual stuff to help people understand what they're looking at, is going to be reusing one of those 3 scales, which is very convenient. If you get the scales right, you can draw the rest of the visualization pretty straightforward. So the first thing we're going to do is we're going to draw the Earth and the Moon. We're just going to append a couple of circles. I even append one for the Moon's orbit using the lunar distance scale. And the Moon's the easiest one to figure out where it is because it's 1 lunar distance away. So you can see that line where it just says lunar distance is equal to lunar distance. And now we've got the Earth and the Moon based on kind of where this would be on the planet. It's right in the middle of the page because we're in the now. And then it's at 0 LDs because the Earth would be considered 0 LDs. We can create these little tick marks to help people kind of guide through to see how that number scales up to 10, 15 LDs as they kind of look down the page. And we could add labels like this just as easily. We haven't done anything with the date scale yet since we changed the X coordinate. So we can bring in the date scale to put a couple labels up top to figure out, offer some guidance of the stuff all the way to the right is going to be approaching within a year, the stuff all the way to the left is approaching a year ago, and the stuff that's kind of in the center over those tick marks are going to be approaching this week. And then one more addition, it's just I find all of the big asteroids that are coming in the future and we offer these little labels. A lot of times you can read about most of the big asteroids that are coming through. There's at least a couple of press releases on the internet through NASA's website or through a handful of other resources. And then a couple more guidelines using all different scales. And the final product ends up looking something like this, which I picked a dark background, which doesn't show up on the screen at all, but space is dark. But one of the really cool parts about working with SVGs specifically, and why I like working with it instead of like a canvas, is most of the stuff is stylable with CSS, which is really nice. I mean, you can change like the stroke from a dotted line to a solid line. You can change the colors and the fills and everything. You could overwrite quite a bit with CSS. So I have a little GIF of the final product where I add a little button to switch it to be on a light background for people who have a hard time seeing this. And it's as easy as adding a class name to the body and then just making sure your CSS is saying, oh, on light background, just override all of these colors and basically reverse it and make it a negative version. I also add a bunch more like little circles and controls to highlight specific asteroids, like especially the big asteroids. There's some URL parameters that you can like set to automatically highlight asteroids that are bigger than like 200 meters, for example. And the interaction, instead of having to mouse over each individual pixel, there's a Voronoi grid on top of it, which is this, I can talk about Voronoi grids for like an hour happily. But the source code is all available on my GitHub page, on the asteroids page, and the actual demo is available at markmarco.com/asteroids if you want to click around and take a look to see if our planet's going to be ending anytime in the near future. And that's it. Thank you.
I had a question set up, but then very last minute, you showed something really cool, which was changing the background to white so it was easier to see on the screen. I think this is something that's really cool about data visualization in the browser versus in like regular PNG or JPEG graphics, is the ability for the user to change what it looks like to suit their needs. Because, I mean, data viz is about telling stories, and you want everyone to like hear that story. What are some other like tactics that you use in making data visualizations to make it easier to read?
I like making the interaction like almost accidental. Like you wouldn't know you could mouse over anything that was up there until you actually like moused over it. And I'm dealing with like circles that have a radius of like 0.75 pixels all the way up to like 5. So they're pretty small, and it's pretty demanding for someone to actually like mouse over, and even especially mobile, like where the thumb, I don't know where the touch would go. So adding the Voronoi layer on top of it to make it just much more clickable, so you can do it on mobile really easily. And I've loaded it up on mobile a ton and done a bunch of testing, and it works really nicely just clicking around near asteroids. And then the mousing over, some people just accidentally will mouse over a certain area and then see it kind of interact, and that will kind of draw them in to do more interactions and learn more about the data set. And I try to find opportunities to do things like that all the time to make it as explorable as possible, but also there's a ton of data we're looking at here. We're looking at like 570 asteroids, and they all have different properties, all different sizes. So it would be a bit inundating to show like a big table or to have like labels everywhere. So we try and pick out, like, I only put labels on the big asteroids, for example. If you put labels on everything, it would just be tons of labels and asteroids and stuff. So you do things like that, just filter out the more important pieces and bring those to light, and then hide the rest behind interactions, and then kind of hope you can lead the user to make those interactions.
Yeah, I think the discoverability makes it a lot more fun on top of like just being interactive. I always like clicking and hovering on things and things popping up and stuff. One of my earliest introductions to seeing data visualizations actually had to do with outer space, and that is the SETI project, the Search for Extraterrestrial Intelligence. Does everyone remember SETI? Still around? You used to be able to like download like a 10 megabyte file, and it would use your computer power in the screensaver to search all this data for if there's intelligent life out there. It costs like the US like a couple of $1 million a year to keep running, and like 10 times as much of that like around the world. And to see stuff like this being done with open web technology, it feels like we can do this cool kind of stuff for already existing problems for pennies on the dollar, I guess. So do you know of any other like projects that are sort of moving from proprietary data visualization and analysis to stuff like what you were talking about today?
Yeah, so there's the New York Times science editor, I think his name is Jonathan Coram. He basically sits on like Mars data and the Kepler satellite data. We're finding potentially habitable planets in the universe, and it's really cool. It just like looks at stars and tries to look for like dips in the light and everything where a planet might be orbiting in front of it. He pulls that data all the time, and he has like a big full page, kind of similar to this data visualization, that's showing like all the stars and all the asteroids as they come, or not the asteroids, the potential planets as they orbit it. And he did a talk at a conference called Visualize, called The Weight of Rain, and it's one of the best conference talks I've ever seen, and I highly recommend looking up The Weight of Rain by Jonathan Coram. He talks a lot about doing just that with NASA's Kepler data, which I thought was really interesting, kind of help inspire this project of space is very hard to visualize because there's so much space. No pun intended. It's just the distances are enormous, so it gets difficult. So you kind of have to just hope that people can understand with the context clues, and I think Jonathan Coram does a really good job with the Kepler project and making it consumable and friendly in a way where it's not just a huge black screen kind of zooming around.
That's cool. I think you should make kind of really a library for people to add to their stuff that has that Y2K check in there. I mean, it's better to be safe than sorry. Yeah, thank you. And I hope that you keep monitoring that data and you'll like tweet at me if something awry is going to happen, so I can get like Bruce Willis on the horn or whatever we do when those things happen. But thank you very much.
No problem. Thank you.